So let us maybe focus a little bit more on the challenging aspects of what there is to be done for the purposes of this lecture. Yet another way of phrasing the issue would be to say, if you're looking for a good, solid problem, quantum gravity may be just for you. Now, part of the excitement of working in this field is really working at the boundary, or perhaps I should say the perimeter, of what may just about still be describable by the tools and methods of theoretical physics. So, we just may be able to push ourselves to the extent that we are able to address some of the issues raised in principle by quantum gravity, but at the same time, we are really talking about a subject that is really currently beyond our experimental reach, or even observational reach in the sense of gathering evidence that might be connected to what such a theory says. Now, what are the questions that we are in principle interested in answering, if only we had such a theory? Well, one issue is, how far can we go back in the history of our own universe to probe the physics that occurred very, very close to the Big Bang singularity, which we believe must have been there? Or for that matter, any other space-time singularity out there in the universe. Can we say something definite about things like wormholes or other exotic space-time structures? Apparently, the answer, if there is one, should be looked for within a theory of quantum gravity. And of course, one question that's really interesting is, what might we, in the best of all worlds, what can we hope to be able to learn? And is it still within the realm of what our methods can, even in principle, cover? Okay, now let us get more to grips with the actual subject matter and start with a wish. So this is what we're looking for, and what we love to have would be a fundamental theory of quantum gravity. Now, I'll often in what follows abbreviate this as QG. Now, what do I mean by this? I mean a quantitative description of space-time and gravity. Well, I often will use these two things interchangeably, on all scales, with particular emphasis on the very short scales, where we believe that quantum phenomena will be important. So let me just write this down. So by this I mean a quantitative description of space-time and its structure, equivalently, well, gravitational interactions on all scales. And of course, it would be very nice if it also did make some predictions, which you can go out and verify in nature. So let me insert a hopefully here. Why do I say hopefully? Well, because we come to that in a second, but if one looks at the scales, kind of the extreme scales at which, at the phase of things, these quantum gravitational effects would be important, they are really very, very far from what we can currently access in any direct way. Now, what will quantum gravity mean for us? we'll basically be after kind of the degrees of freedom that describe space-time and gravitational interactions on the very shortest scales. Now, as a matter of principle, these might be closely related to what we perceive as the classical degrees of freedom that are familiar, of course, since they underlie general relativity. But in principle, that could be something quite different. Whatever it is, whatever its dynamics is, by whatever equations it's being governed, that for us will constitute kind of quantum gravity. And of course, by saying that, I take a reductionist point of view, because I'm asking, how are phenomena, gravitational phenomena that are described even on large scales, I mean everyday scales or even larger cosmological scales, can they be ultimately understood in terms of some microscopic theory and certain dynamical laws? So whatever this is, so and I think I'm postulating there is something of that nature to be understood. There is something of that nature there on these very shortest scales, although I currently have no way of directly looking there. So quantum gravity, you could therefore also say, is my search for Planckian. Now, the Planck scale, also we'll get to, is kind of the characteristic physical scale on which quantum gravity, at which quantum gravity should be relevant. So Planckian or sub-Planckian, so that means even smaller length scales potentially. DOF stands for degrees of freedom. And their dynamics is what we are primarily going to be interested in. Now, once again, it's unclear which part of the ingredients of the classical theory will remain relevant and interesting when we get to these very, very short scales. Are the classical, concepts we classically take for granted, of course, if you're kind of thinking of kind of a smooth space-time that is maybe curved, but it has certain properties like, causality. It makes them meaningful. There's a time-like directions, there's space-like directions. Of course, these are things that are also still there in general relativity, but do they continue to be meaningful concepts on very, very short scales? Or are they perhaps just emergent phenomena on a larger scale of some underlying microscopic quantum dynamics that may, at the first glance, not at all look like classical gravity at all? So there clearly, these possibilities exist. And at this stage, of course, I should also say the theory is clearly in no way understood with any degree of completeness. That also means, of course, when there is a great deal of uncertainty as, to some extent what one wants to achieve, what precisely one is looking for, what the structures should satisfy one is looking for. So it's not, it's of course, as I said already, it's not related directly to experiments and observation. So there is also a clear danger of just going wrong or barking up the wrong tree. And there's also, that's of course something that can be generally said about, say, physics beyond the standard model. And of course there is a danger in that field of going astray and even going en masse astray in one direction or other. So these things one should keep in mind. And in a way, they raise a new question that if I'm in a situation like that, where I really want to describe or understand, to start with kind of theoretically, physics that might be going on these very distant extreme scales, how do I go about it? How do I make, can I put in some, security, in how I do this? Can I put in, can I do this that ensures that, well, if, of course, I can go wrong, but can I take approaches that make whatever I'm deriving reasonably robust? So I can be at least reasonably sure that, some outcomes of hypotheses, calculations are generic rather than relying on assumptions upon other assumptions. And then, of course, might have a high degree of likelihood of being wrong in the end. Okay, now, that's clearly something that is not totally specific to quantum gravity, but of course quantum gravity is an important part of theoretical high-energy physics that we haven't yet understood, and that goes beyond the standard model. Okay, so just to fix this in writing, so we have to deal with a particular situation where direct experiments or observations that might, in principle, of course, guide our theory building are currently absent. And that's clearly a drawback. And that will be, and this will clearly put some people off, looking at it at all or finding it interesting at all. Now, what's the aim of my lectures? Of course, a lot of that, as I said, is working at the perimeter. But of course, in order to be able to do that meaningfully, you have to understand elements that are present in the classical theory or, say, in the perturbative quantum theory. So there's lots of things one has to know, and you won't, at your stage in your careers, know. And I have to take this into account when teaching the subject. That will have to do, of course, with classical aspects of gravity. So in my lectures, I'll be going back and forth between kind of reminding you of certain classical concepts, where reminding may sometimes also contain just completely new elements for some of you, and the aim of what one wants to do in the quantum theory, which is just to construct the true kind of the quantized theory of the gravitational degrees of freedom, which we believe should be out there. So what I can do here is, in these 3 weeks, it's not a lot of time, give you a guidance to what this is all about, the kind of things that people have tried, how one can roughly kind of categorize different ways of going about trying to find the quantum theory of gravity, what the difficulties are when one tries to do this, and how one might address these difficulties, what one has learned, and where we stand. And of course, it's a big, big open end, as I already said. And of course, I cannot possibly be kind of comprehensive or even give you a comprehensive overview. That's a subject matter that people have worked on for several decades, and rather clever people have worked on. So I can only give you, an overview, and here and there, glimpses. So you try, so some first picture about the subject will hopefully emerge for you, and you can decide for yourself whether you find it interesting or maybe not so interesting. Now, why do we believe that a quantum theory of gravity should really be out there, for us to find or discover, or what have you? One way of phrasing this is to say, well, if it weren't there, then some fundamental things we believe we have learned from 20th century physics, would have misled us or would be wrong. And let me phrase this as saying both quantum theory and gravity are, in slightly different ways, universal in character. What do I mean by this? Quantum theory is, whenever we're looking at interactions described in nature, if we only look close enough, which often means on sufficiently small length scales, we discover that the physics is governed not by classical laws of motion, but by quantum laws of motion. A prime example would be electrodynamics. Right? Of course, there are phenomena that are perfectly well described by the classical field theory of electrodynamics, but when you then start looking at interactions at molecular, atomic, even smaller scales, you find that the classical description does no longer suffice, and you have to work with the quantum theory. So in that sense, we think of the quantum theory as being the real theory. and of course at sufficiently large distances, or when sufficiently many particles are involved, the classical description may be perfectly fine, but it's not. The more fundamental description is the quantum description, of course, and certain mathematical structures that go with that quantum description, and certain things that we think of as ingredients and fundamental ingredients, and laws are of a quantum nature. Now, gravity is universal in a different sense. So it seems to be the case that all forms of matter and energy exert and and can feel gravitational forces. So whatever there is in terms of energy out in the universe, it will create a gravitational field that is felt by everything else in principle that has matter or energy. So there's nothing that escapes gravity in that sense. So everything interacts in some way gravitationally. You know, you and I, we interact just by virtue of having a mass gravitationally. Of course, often these forces are tiny, tiny, but nevertheless, you know, there is no way of shielding yourself from them. So we have these two types of universality which permeate, of course, physics and the way we think about it. And kind of putting one and one together, since we have a classical theory that describes very well gravitational interactions, well, you know, if it behaves like all the other theories we know, there ought to be a quantum theory that is more fundamental. And it's a meaningful question then to ask, well, what is it? And what are its fundamental degrees of freedom? Now, the fact that we don't yet have such a theory, of course, indicates also that, well, there is maybe a problem compared with the other theories that goes beyond there being no experiments and observations to guide us. And that lies very much in the nature of already what classically this theory is and describes. So one way of formulating this is to say, let me just move this to here, is to say, now, what do I want the quantum version of? And then, of course, I start out with classical gravity, or general relativity, which I abbreviate GR. So I use this interchangeably. So what does one try and do there? Well, the central aim is, of course, one has a bunch of partial differential equations, which are coupled, and these are the Einstein equations. So, one wants to solve them subject to certain boundary conditions and maybe a matter content of a piece of space-time or even the entire universe. So, you know, it's something concrete to do. You have these equations, and you solve them. And what comes out? Well, what comes out is a configuration of the metric tensor, you know, the G mu nu of x. And then that describes for you a space-time. Now, what's a space-time? A space-time is, well, you might say a configuration in a classical field theory that describes to you how curved space-time is at every point. And of course, curvature we can detect in the usual ways, and that's something you learn in your GR course by Watson clocks or sending light signals, and you have things, objects moving. I mean, parallelity becomes a different notion. I mean, that's just what, you know, GR Einstein theory is all about. So, in a nutshell, we are trying to solve Einstein's equations. And this will give us possible spacetimes, the outcomes. There are solutions to these equations, and if you haven't seen them written down, here they are. R mu nu, curvature tensor, minus 1/2 G mu nu R, plus, let me introduce or include a cosmological constant term, just for generality. It's equal to 8 pi Gn T mu nu. And I guess you've had a relativity course and you have seen these equations. Yes? Yes, good. So it's not mystery what these symbols mean. Now, one way to say, well, what is quantum gravity about? It is really, well, trying to look for quantum analogs kind of the classical Einstein equations and solve those, again, of course, subject to boundary conditions, etc. And then what comes out, the solutions should give you, well, they should be kind of quantum spacetimes, I could say. So spacetimes which describe also kind of the quantized degrees of freedom underlying the classical configurations that entered in here. So what I mean, and let me put kind of this in inverted comma. Let me call this kind of quantum Einstein equations. Which I want to be understood in a quite general sense as some kind of dynamical principle, well, which one, nevertheless, has to solve. So there's something one has to do to solve the theory. Now, what's the analog here? Well, we don't really know. Or rather, you know, it's not quite as bad. There are various suggestions of which dynamical principles or what types of equations you know, might be appropriate here. And that's, of course, part of what my lectures will be about, to introduce you what the possibilities are here. But outcome should be kind of realizable, I mean, possible quantum spacetimes. Sometimes abbreviate these ST and QST, but just for the purposes of this current present lecture. So that's, roughly speaking, you know, one way of thinking about it. So I have to find some quantum dynamic equations. I have then to solve them, and then, whoops, I have a solution to the quantum theory. Now, what is somewhat special about the role of space-time, and that's of course already true at the level of the classical theory, is that space-time itself is dynamical. I mean, the metric is just what describes space-time. That's something that's the subject of these equations. So, of course, the G mu nu is, of course, here. The G mu nu and its derivatives in the curvature sit in the curvature tensor. And that's, of course, different from other theories where you have a fixed metric background and then you have a specific field content of stuff that lives on a given space-time. Now, here we are looking for what is space-time itself at the classical level and at the quantum level. Well, that's also, if I now think about the quantum theory, that brings us to why it is more difficult to come up with a good quantum theory for gravity than it is for the other interactions. So in the other interactions, space-time is kept fixed. Although I should emphasize, usually kind of the structure of space-time, usually flat Minkowski space, is very, very crucial in how we formulate, address, and solve quantum field theories. Now, it's almost invisible because you don't much talk about it, but if you study relativistic quantum field theories, of course, there are many entries to the subject, but of course, you have also already taken a course in that, then one very crucial feature is the symmetry structure of that space. So that are Lorentz transformations, I mean, in relativistic quantum field theories, which one looks at, and associated, if you add the translations, Poincare transformations. And why are they so essential? Because, for example, we can classify particles and fields according to how they transform under these transformations. And the symmetries are only there. They're only there because the underlying space is Minkowski space, and it has a certain symmetry. So there are things I can do, global transformations I can have on that map that Minkowski space into itself, that R has a physical interpretation of changing inertial system, that leave the physics invariant. And depending also on how a certain field transform under these transformations, the Poincare transformation, I can classify them, and then I just get the classification according to mass and spin. Now, the moment this background Minkowskian spacetime is absent, much of that goes completely out of the window. And of course, symmetry is something you very crucially use always as much as you can in solving a given theory. And we make very crucial use of it, I want to say, in standard quantum field theory. Then the question poses itself, now, if such a symmetry structure is absent, well, what remains? What can I still use of my standard machinery also to construct the quantum theory? And that's already quite non-trivial if you have a fixed but curved background spacetime, say, on which other fields live and interact. That already, because that is in general not Poincare invariant, because it's not flat. But yet another step is what happens if the spacetime is not only curved, but can also quantum fluctuate. And that is, of course, the case here. Which of the usual, the standard techniques of building up quantum theories, quantum field theories, are still valid and can still be used. And it turns out, well, not so many, as a matter of fact. And that exactly is what contributes to making this a really hard problem. Writing down quantum dynamical principles, quantum dynamical equations, and then subsequently solving them. So that gives you a first glimpse of why this is a non-trivial enterprise. Now, one thing that is clear that has to happen, if I look here at these two steps, now, the classical theory is certainly well known and also well tested in its range of applicability. That means sufficiently large length scales, so above millimeter range, very roughly speaking. Now, quantum gravity should describe the same or related degrees of freedom, but at much, much smaller scales. But whatever it is that the theory describes, if I take an appropriate limit, say of large length scales, then this better re-emerge, or the classical limit should better be the theory which I already know to be the appropriate description on large length scales. And in principle, you can use this. This is certainly a necessary condition any quantum theory of gravity will have to satisfy. If I choose my scales classical in that quantum theory, of course, a quantum theory in principle is a good theory for all scales. But if I put explicitly in large scales, the classical Einsteinian theory should re-emerge. The classical spacetimes should re-emerge. So let me just add this here as a note. So what we need is that, given quantum gravity and solutions that are some quantum spacetimes, if I take here some suitable classical limit, GR and classical spacetimes and spacetime solutions should re-emerge. No, I'm not doing this well. Yes. Now, what I'll do also here, and what I like to is just draw a little picture of scales, physical scales. Theoretical physics might want to talk about. And of course, theoretical physicists are nothing if not ambitious. So we start, I can only put it on the board on a logarithmic length scale. sensibly, and let me not go across the whole board, let this be a logarithmic length scale in meters, so some powers of meters. Let this be 10 to the 24. What is 10 to the 24? That is the radius of the visible universe. So everything that we can currently kind of see. In principle, now, that's of course vast scale. This is kind of all of cosmology. 10 to the 0, that's us. Now let's see. Does it about work out, relatively speaking? Yeah, about. So this is 10 to the minus 35. That's the famous Planck scale. I'll get to that. Now, here, let me put this a little bit to the right. Here. So these are atomic scales. Let me indicate it like this. Now, what scales can our best particle accelerators currently probe? About 10 to the minus 19 meters. So that's about the length scale kind of gluons, roughly speaking. So this is kind of the LHC, gets us to here. Some other processes in nature which you can observe have even higher energies, and ultra high energy cosmic rays are of that kind, so they get us to somewhere around here. So these are ultra high energy cosmic rays. And what we are interested in here is this scale, Planck scale. So that's the Planck length here. Oops. That's the region we are interested in. So this here is the visible universe. Now, let us ask ourselves, so what is the role of gravity as one of the 4 fundamental actions, depending on where we sit in on this scale? Now, this here is the realm of, entire universe, galaxies, etc., clusters of galaxies, largest known visible structures in the universe, planetary systems about here. And in this range, GR seems to be a perfectly good description because, of course, the so-called standard model of cosmology is, of course, directly under with certain additional simplifying symmetry assumptions derivable from general relativity. So here, apparently, GR is both relevant, gravity, and, well tested. So this kind of classical GR. Of course, modulo the small things that kind of 95% of the stuff we have to postulate to be there in order to actually generate kind of the large-scale structure and dynamics we see of our own universe, is unknown stuff, dark matter and dark energy. So with this small proviso, classical GR seems to be a perfectly good description on these length scales. Now, if I go to smaller scales, atomic scales, subatomic scales, kind of particle physics scales, well, what happens to gravity? Well, gravity apparently is completely irrelevant. And why is that? Well, because it is so much weaker than the other 3 forces. Of course, on larger scales, electromagnetism, but then, of course, also going to smaller scales, the nuclear forces, weak and strong. They are enormously much bigger by so many orders of magnitude. I believe there might be an exercise for you to work out how many. So gravity loses out. There is just, forget about gravity everywhere here. So apparently gravity doesn't play any role whatsoever. So let me write it like this. I mean, in the sense I just said, I mean, on short length scales, so gravity apparently is unimportant. Let me put a little question mark, but that's what seems to be the case on the face of things. Now, this is the Planck scale, and what defines the Planck scale? The Planck scale is the scale, dimensionful scale, I mean, it's a length scale, the unique scale which you get by putting together three fundamental constants of nature, which is G Newton, governing, of course, the strength of the gravitational interactions, the speed of light c, governing kind of relativistic phenomena, and h bar, of course, expected to be prominently present. So a region where all of these kind of three couplings come in naturally is of the order of the Planck scale. So if you put that in numbers, so the Planck length is obtained by kind of the unique dimensionful constant of the dimension of length you can obtain by putting these three constants together, G Newton, h bar, and the speed of light. And if you evaluate it, it just comes out to about 10 to the minus 35 meters, as I indicated here on this scale. Now, the reason for why this Planck scale is so small is because of the weakness of the gravitational forces. So because of the smallness of G Newton, you could say. Right? So that because that is so much smaller than the constants that govern the other interactions, this quantum scale is so much lower, is so much smaller also. So it's in the nature of these gravitational interactions as we find them in nature. So that's what we are given. It's not what we asked for, but this is what we were given. That's how nature seems to be. And now I'm rapidly running out of time. Oh no, I'm not running out of time because I didn't start on the full hour. So I still have plenty of time to give you my, the gravity being weak demonstration. So here, I saw Lisa Randall do this on TV, and I thought, I can do this too. Now, this is a magnet, okay? Small magnet. This is a paperclip. It's magnetic. So now, the point is, there is now a competition of the force, electromagnetic force exerted by this tiny, tiny magnet, competing with the gravitational pull exerted by the entire Earth below me. And they're competing, for this little paperclip. And, see what happens. See? All the mass of the big Earth is unable, to compete with this tiny magnet. So this is just, to give you a feel of how weak gravity is. Of course, we don't think of it this way because often, and say, when we get to cosmological scales, gravitational forces are, of course, totally dominant. I mean, they just determine, basically, the large-scale dynamics of the universe. Now, why is that? Well, the point is, of course, electromagnetic forces are also long-range, just as gravity is, but you have, of course, negative and positive charges. And on large scales, these tend to neutralize each other with no net forces. That's not true for gravity. Gravity is always attractive. Right? So on large scales, gravity always wins out, even if it's tiny, looked at kind of locally, and locally on small scales and very small scales, it has no chance. But going to large scales, it wins over. Yes.
So there are these units where h bar, c, and
Yes.
How can one see that gravity is weak in, say, such a
well,
system?
Yeah, this is of course just a convention. And the convention is a suitable convention, of course, when you're planning to play around with phenomena that live on that scale. If you keep working in these natural units, then you have a lot of zeros to carry around with you. So you're right in the sense that it's a convention that is misleading. When you maybe open for the first time a textbook and don't realize, well, how tiny all these numbers are, because people, omit this, they set things to 1. Well, but of course, it's done in such a way that whatever expression you look at, there's a unique way to restore these units. And once you've done this, you see, oh, this is a very small term, right? How on earth am I ever going to measure this or observe this? So we are collectively maybe also partially fooling ourselves by choosing such units. But of course, it's to be understood. These are the natural units for someone working in quantum gravity who is, of course, well aware of the weakness of these effects, or ought to be. Now, where was I? The weakness of gravity. Well, does this also mean there is no hope for us to ever detect such phenomena? Clearly, I mean, we are 16 orders of the LHC is 16 orders of magnitude away from that scale. From that, one would say, well, probably if you just extrapolate current, technology or well, the approach of banging things together with more and more energy, we are not going to get there. Of course, that doesn't exclude that there are not already now perhaps data we could gather, say observational data we could gather kind of astrophysically, that carry a trace of quantum phenomena, right? Of stuff that happens on these tiny, tiny scales. What you need in order for such a thing to be out there, you need some kind of magnifying mechanism, right? And of course, such things could be present. For example, one example is, of course, if the universe was in a very highly, quantum phase, very close to the Big Bang, if these signals could find a way, to our current scales in some way or other, being not interfered with by, some soup of other stuff that, of course, surrounds this, then we might see even traces of quantum gravity in something like the CMB today. I'm not saying we are there yet. That's just, of course, a hope one can have. But clearly, there is something also, as I said, some kind of magnifying mechanism that must get us away from these tiny numbers, these tiny, tiny effects. It could also be something that people have speculated on, that imagine a kind of a light ray that reaches us from very, very far away, the edge of the visible universe. Now, if I postulated, for example, there might be some non-trivial structure at the micro level of space and time, which has a tiny, tiny, tiny effect, but might be picked up in a cumulative way by the light ray that has been propagating for, don't ask me how many zillions of light years, to come to us, say. Could there be, say, in the dispersion relation for such light rays, might there be a trace of quantum gravity? So this is something one can hope for. One can maybe, if one has a theory, might be able to make an estimate for and then look for it in nature. So it's not completely beyond reason that such effects exist, but we are not quite there yet, even at the theoretical level, to say, look, this is what we should be looking for. This is a clear quantum gravity signal. So that's a bit of an uphill battle, but there is a field that is called quantum gravity phenomenology. And that is just a dedicated search for what kind of effects might in principle be out there. It's a true challenge because of the tiny, tiny scales involved. And yeah, I could say it's a nascent field, but probably it will be nascent for some while still. As we get to grips with how possibly, if we have a theory, I mean, how possibly, what might its physically observable consequences be? And of course, there better be something like that in the end, because otherwise it will just, remain metaphysics and not physics. Yeah, so that is more or less, that covers my introduction and motivation. Now, what I want to do very briefly is just flash a few symbols on the board, just to remind you, what's a classical what are the interesting objects one looks at in the classical theory. Of course, the Einstein equations are already up there, but also remind you of some of the classical properties, some of which make it so difficult to come up with a good quantum description of that classical theory. Now, let me start by making a few statements about the classical theory. So what I, right at the beginning of my lecture, already alluded to is this kind of the nature of gravity. First of all, its universal character. And the universal character actually makes it possible that we encode the presence of gravitational interactions into kind of the local structure of space-time itself. So Einstein basically gave us this formulation that says, well, all masses, all forms of energy, mass, etc., interact, but since there's no escape from gravity, I might just as well encode these interactions into what I call the curvature of space-time. So in a way, space-time structure is just the same as gravitational interactions. And I can probe, of course, the space-time structure, as I said before, like by test particle, for example. So gravity, this can be captured by kind of the one-liner, saying gravity is space-time geometry. So I have this dual way of thinking about the theory that is often useful, but also, of course, just characterizes the theory in some very fundamental way. So here, just to recap some of the basic ingredients and to fix some conventions. So the metric field tensor is G mu nu of x. So that's a Lorentzian signature symmetric 2 tensor describing, of course, measurements of angles and distances in a 4-dimensional sense, and for a Lorentzian signature metric. And my sign convention is that of general relativity, usually chosen. So time with a minus sign and spatial directions with a plus sign, opposite of what you usually do in QFT, particle physics. And, well, we have this beautiful quantity called the infinitesimal line element, ds squared, G mu nu of x, dx mu, dx nu. Now, this is a nice equation because it captures some of the essence of the theory. Well, you can say, well, it just gives me G mu nu of x, and already I wrote down G mu nu of x here. Well, that's not how we should think about this equation. So you should think about this equation as giving you this infinitesimal line element that has an invariant meaning in this Lorentzian. So it's kind of an infinitesimal distance squared that is kind of a physical kind of invariant thing that all observers will agree on in a way. Now, what appears here on the right-hand side is an explicit coordinate system. So the thing is that in GR, we are allowed to pick any coordinate system whatsoever. And the way to think about this little equation is to say, I've chosen coordinates x mu here. That means that the invariant geometry this kind of the left-hand side here, the invariant distances, are given in these coordinates by this g mu nu of x, where the emphasis is on, well, if I had chosen some other coordinates, you know, dy or y with differentials dy, some other coordinates, this would be a different metric, potentially, but leading to the same, you know, invariant distances on the left-hand side. So the g mu nu, if you like, is what translates between your arbitrary choices of what you call x, you know, in the x0, x1, x2, x3, in the direction of, and coordinate distances, what translates these and the arbitrary choices that lie behind this to invariant distances. And that, of course, also means that the same geometric space has lots of different explicit descriptions if you refer to explicit coordinate systems, right? And in a way, you can be misled by thinking that all kind of these numbers, this bunch of numbers that sit in these centers, they're all physically distinct. That's not true, because there's a large redundancy in the theory that comes from choosing different coordinate systems, which on the face of it lead to different metrics, but in reality correspond to one and the same physical space-time geometry. So I want to emphasize there's a large redundancy, which you can think of as a gauge redundancy, a little bit like in local gauge field theories, that make that not all degrees of freedom that in this g mu nu of x are actual physical degrees of freedom. Now, the formal starting point of the theory, usually in the classical theory, is a differentiable manifold. And a notation I'll use is M, and 4 just indicates the dimension of it. And the topology of this space, classically, is usually chosen to be product topology. So R kind of is a corresponding to the time direction times some topology of the generic, spatial slices. And you could have many choices here. That could just be open, and it could be an R3, it could be an S3 if there were compact slices. So many choices are possible for the spatial slices. Interesting things, of course, derived quantities from the metric are, amongst other things, the Levi-Civita connection, things like the Riemann tensor, R, K, lambda, mu, nu, contractions of the Riemann tensor like the Ricci tensor, R, mu, nu, and contracting that with the metric, of course, you get the Ricci scalar. And so what you do now in this classical setting, you would always have kind of to make explicit a little bit the remarks here I made about choosing different coordinate systems. So you have some differentiable manifold M. And, well, let's look at a little patch of M at the neighborhood U of some point P. Now, what you do is, by choosing coordinates, is, well, you put like a grid locally on a neighborhood in order to be able to label points uniquely, right? In order to be able to refer to individual points. So a more abstract way of thinking about it is that, well, that is a map, x mu, that maps you from, at least from a region of the spacetime M, into an RD, an R4 in our case, because the original spacetime was 4-dimensional. So every point here will now have an image point in this space R4, right? Some coordinate assignment, you could say. So let this be the point x mu of P. And then this, where is my point? It has disappeared. Here's my point. And let this be kind of the image of this U. Yeah. So this is called also a local coordinate chart. And this picture is again helpful in underscoring that the way in which I make this identification is just to a large degree arbitrary. This is a real thing, and this might be a piece of curved manifold, might have certain metric properties. I'm going to an explicit chart in order to be able to write down these quantities as tensors with explicit entries and explicit dependence on the metric. Now, the invariance under choice of coordinate system to describe this also goes by the name of diffeomorphism invariance. So it can be thought of as invariance under choice of coordinate system. And I would say one difficulty in the quantum theory is kind of, well, how does this make an appearance, and in which form does it make an appearance? How do I handle this symmetry in the quantum theory, this redundancy? And it's, in a way, yeah, one is unhappy with having to make such a choice. Of course, it enables one to do calculations on the one hand. On the other, it introduces this enormous degree of redundancy in the theory, which one has to keep at the back of one's mind, that is there. To finish, just let me orally give you a brief overview of what I intend to cover in the remainder of these lectures. I basically, I've ordered things in 3 blocks. Now, in the first block here, we'll be talking about standard perturbative quantization of gravity as a field theory. So, in a way, we'll be talking about linear gravity, about gravitons, and also in how to formulate a path integral for these fields. So that's an extension of some of the stuff you've probably learned in your QFT courses. Yes, applied to the metric field. What we'll do, well, and then I will outline difficulties. I explain you why this has difficulties, essentially because the theory turns out to have incurable divergences when you look at it this way. Alternatives we'll look at in week 2 and 3, and they are so-called non-perturbative ways of quantizing gravity. So that means don't do it the perturbative way because something went wrong with it. Of course, I will explain to you what one means by non-perturbative. And here one has 2 different ways of going about it as a technical calculational scheme. One can either do it the canonical way, that means a canonical quantization which uses operators, wave functions, Hilbert spaces, quantizations of classical Poisson algebras of interesting objects you have in gravity. And what kind of quantum theory can come from that? And there is the kind of complementary way of quantizing things the path integral way, but also non-perturbative. So what has been done there and how the problem is formulated, we look at in week 3. There is no literature, good literature, I can recommend, apart from perhaps this book I've also recommended in previous years by Klaus Kiefer. It's called Quantum Gravity. It's a quite comprehensive overview of all different approaches there are in a nice and systematic way. So it covers a lot of ground, but it also, of course, has introductory chapters where motivation is given. So there are, of course, many other books that specialize maybe then on a particular approach, but for the general picture and for someone who wants to learn about it, I'd recommend this book. I guess there will be also notes online, etc., and more tips on what to. Klaus Kiefer. He's a professor in Cologne in Germany, and this book is based on lectures he gave. So it's just an elaborated, of course, much elaborated version on some lectures he gave himself. Very good. That was the first lecture. I see you back tomorrow.